All right, today we're going to tackle one of the most elegant and honestly most important equations in all of physics, the wave equation. We're going to start with something you can actually touch, a guitar string, and see how that connects to a law that literally governs the universe. Okay, let's get into it.
So, you've got a musical instrument, and then you've got the cosmic speed limit. What on earth could they possibly have in common? Well, the answer is a single, incredibly powerful piece of mathematics that we are about to unpack. And we're going to start this whole thing off not with some scary abstract formula, but with something simple and tangible. Just imagine a single vibrating string. That's it. That's our starting point for understanding something truly universal. You know, this is a classic move in calculus and physics. If you want to understand the big picture, you've got to zoom way, way in. We're going to analyze the forces acting on just one tiny, infinitesimally small segment of this string. That's how we're going to build this entire equation, from the ground up. Okay, so now we take that physical idea, the wiggling string, and we translate it into the language of mathematics. And to do that, we're going to pull out one of the most famous tools in the physics toolbox, Newton's second law. You know the one. Force equals mass times acceleration. So here's our game plan. It's pretty straightforward. First, we're going to grab a tiny little piece of the string. Then, we figure out the forces pulling on it, specifically the tension yanking on it from both sides. And finally, we just apply Newton's second law, setting those forces equal to our tiny segment's mass times its acceleration. It's a really powerful and logical way to build this thing. Before we jump into the equation itself, let's meet the main players. We've got T for tension. That's easy enough. Rho is its density, basically how heavy the string is. U is just the vertical position of the string at any point x and any time t. Now these last two are the fun ones. They're partial derivatives. UTT is its acceleration, right? How its position changes over time. But UXX, that describes its curvature, basically how bent the string is in space. Keep that one in mind, it's super important. So you take Newton's law, you sprinkle in a little bit of that calculus magic, and when the dust settles, all those physical pieces come together to form one single, incredibly powerful equation. And here it is, the wave equation. So what's it actually saying? Well, it tells us that the acceleration of any point on the string is directly proportional to how curved the string is at that exact same point. And that proportionality constant, it's c squared, the speed of the waves squared. It's so cool how the physical stuff, the tension and a density, directly tells you how fast the wave is going to travel. Okay, so we built it, that's great, but an equation is pretty useless if it doesn't actually work, right? So how do we know we got it right? Well, we test it. We're going to take a couple of functions that, look like waves and see if they actually solve our equation. First up, let's try a classic, a traveling wave. This function here, u equals sine of x minus ct, describes a perfect sine wave that's just cruising to the right at a constant speed c. So, does it fit? Let's find out. So, to check this, we've got to do some calculus. We need the second partial derivatives. So on the left, we differentiate with respect to time, t. The derivative of sine is cosine, and then the chain rule tells us to multiply by the derivative of what's inside, which is negative c. We do it again. Derivative of cosine is negative sine, and we get another negative c. So that's where the c squared comes from. Now for the space side, with x, it's actually a bit easier because the derivative of the inside is just 1. You can see the results right there.
Okay, the moment of truth. Let's plug what we just found back into our big wave equation. Does UTT equal c squared times UXX? And would you look at that? Yes, it does. Both sides are a perfect match. So check one. Our equation definitely describes a traveling wave. All right, let's try something different, a standing wave. Now look at this function. See how the space part, sine of x, and the time part, cos of ct, are separate? They're multiplied together. This is a super common way to solve these kinds of equations, by the way. It's a method called separation of variables, where you basically guess that the solution is a product of two separate functions, one for space and one for time. So we do the same thing again. Take the second partial derivatives. For the time derivative, we pretend sine x is just a constant number. The derivative of cos ct spits out a negative c twice, so we get that negative c squared factor. For the space derivative, we do the opposite. We treat cos ct as the constant, and the second derivative of sine x is just negative sine x. Pretty clean, right? And you guessed it, when we plug these new derivatives back into the wave equation, it works. It totally works. This is amazing, right? We have one equation that can describe two completely different kinds of wave motion.
Okay, so we just proved that two functions that look totally different are both perfect solutions. But what does that mean in the real world? Like, what's the actual physical difference between these two waves? Let's really break it down.
And this really lays it all out. That traveling wave, the one with sine of x minus ct, its whole shape it moves. It travels down the line. But the standing wave, sine of x times cos of ct, it doesn't go anywhere. Its shape is locked in place by that sine of x part, and the whole thing just oscillates up and down, kind of like a jump rope, thanks to the cos of ct part. And that brings us right back to where we started. We began with a simple guitar string, but we've uncovered a law that is truly universal. I mean, this exact same equation describes the sound waves coming from that guitar. It describes ripples on a pond. It even describes light traveling from stars billions of light years away. It's just this beautiful piece of math that ties so much of our universe together. And it really makes you wonder, what else does it describe?